Like, let's see some of these practice questions on lens, on light, waves, refraction, mirrors, and waves generally. So this one says a converging lens has a focal length of 7.0 centimeters, a height of 2.0 centimeters, and is placed 3.0 centimeters from the center of the lens, and is a full-scale grid shown here, all drawn to scale with the arrangement. So basically what it's telling us is this is the object, this is a principal focus on one side, the principal focus on the other side, and there's the lens. The question requires us to, by drawing on figure 7.1, show how the lens forms an image of the object, and then we state two features of the object, of the image. Two features only. Excuse me. So we start with one of the principal rays. I can use a red marker, a ray that is parallel to the principal axis. Once it gets to the vertical plane of the lens, once it gets to this vertical plane of the lens, the ray will bend and pass through the principal focus. So we show arrows. I can draw the second ray with a green marker or even a blue marker. Okay, let me use a green marker. A ray that passes through the geometrical center. The one that passes through the geometrical center doesn't bend, it just goes straight. As you can see, these two rays will never meet. Now, since they cannot meet, it cannot meet, so it can't form real images. So we need to make the rays longer to see where they will appear to meet. And draw this one too to see where it will appear to meet. Now where these two rays appear to meet, remember these are virtual rays, they don't actually meet at this point. That's why I showed them with dotted lines. So here that the rays appear to meet is where the image is formed. The image is formed here. So we can draw the image. Let me use a blue line to draw the image. The image is formed here, where the rays appear to meet. As you can see, the image is upright. That's the image, whereas this is the object. And you can see that the image is bigger than the object, so the image is enlarged. And of course, it is virtual because the rays do not actually meet here. So we can write the features of the image. The image is upright. Image is upright. Image is upright. Image is upright. Image is virtual. You may include images magnified or enlarged. It says determine the height of the image. All we need to do is to measure this distance from here to here and show the value. And then it says state the name of one device where a lens is used in this way. You can see the image is enlarged or magnified. So this can find practical application in magnifying glass or simple microscope. So magnifying glass, or simple microscope. Simple microscope. Magnifying glass or simple microscope. Alright, so the next question says, I think the next question looks similar. says an object is placed 3 centimeters from the center of the lens. This is the geometrical center of the lens of a convex lens of focal length 6 centimeters. So we just measure 3 centimeters and place the object of any height, and also measure 6 centimeters for the focal length, maybe here, focal length on one side, measure 6 centimeters again, focal length on the other side, and then it says an enlarged image is observed. By drawing that, we also see the enlarged image, just the same way we did for the other one. So it says state why this image is called virtual. It's called virtual image because the rays do not actually meet where the image is from, so it cannot be captured on a screen, like we already discussed about virtual and real images. Real images can be captured on a screen because the rays actually meet there, but virtual images cannot be captured on a screen because the rays do not actually meet where the image is from. It says state the common name given to a convex lens used in this manner. Well, you can talk about magnifying glass. It's also magnifying glass. Or simple microscope is the same thing. Next question says, figure 6.1 shows 2 rays from a point object incident on water surface. An observer sees the image of P produced by reflection on the surface of the water. So this is where the observer sees it, by reflection. So of course, if it is reflection, one ray strikes the surface of the water and reflects. The other ray strikes and reflects, and they will not meet because they spread. So an observer whose eye is here, we see the image appearing to form where the rays meet. If you take the previous lesson or what we said earlier on, when you draw these, they will appear to meet at a point. Wherever they meet is where the image is from, but you can check the previous lesson. It's exactly the same question. It's a similar question. Then it says on figure 6.1, draw all that. We've done that. Just a guide. It says on figure 6.2 shows 2 rays from a point object Q incident on another water surface. An observer sees the image of Q produced by refraction. This one is by refraction. You know, for refraction, a ray moving from more dense like water and going towards air will bend away from the normal. So this one will bend away from the normal. This one will also bend away from the normal, but they will never meet, and the line will appear to be coming from a particular point where the virtual image is formed. And that virtual image is the apparent depth of Q, where this position is the real depth. Where the virtual image is formed is the apparent depth. We have discussed this in the previous. Discussed that earlier. Now, another part of the question says the refractive index of water is 1.33. Calculate the critical angle. You know, the formula is refractive index is 1/sin of critical angle. We can find out using that formula. Now, it says describe with a diagram the medical use of optical fibers. Optical fibers can be used in endoscope, the instrument that doctors use to observe the internal organ. And we've discussed how optical fibers work. You can find that in the previous lesson. Okay, now this question says, let me read it out, zoom in a bit. Figure 7.1 shows the principal axis PQ of a converging lens and the center line XY of the lens. This is what it's talking about. This is the lens itself, axis of the lens, and this is the principal axis, PQ. In other words, this is the vertical plane of the lens. This is the principal axis, PQ. And it's a converging lens. It says an object of height 2 centimeters is placed 2 centimeters to the left of the lens the converging lens have a focal length of 3 centimeters. So all we need to do is to place an object of 2 centimeter, or object of height 2 centimeters, 2 centimeters from the geometrical center. The geometrical center is around here. So if the object is placed here, the height of the object is 2 centimeter and it is 2 centimeter from this. And then of course we also indicate the focal length. We are giving the focal length. The focal length is 3 centimeters. So we also indicate 3 centimeter to the right, 3 centimeter to the left, and we follow the same procedure to get the position. The next question says, on figure, draw a full-scale diagram to find the distance of the image from the lens and the height of the image. All of that you can just state and explain whether the image is real or virtual. If the rays actually meet, the image is real, but if the rays do not meet, the image is virtual. Now this question is, a ray of light from a laser passes from air into a clear semi-circular plastic block. The figure shows the ray from here, it passes into here. Then it says, the ray continues in the same direction and meets the middle of the opposite surface phase angle at 40 degrees to the normal. The refractive index is 1.5. The ray continues into the air. Calculate the angle between the normal and the path taken by the air after it leaves the block. So of course, when the ray moves from the glass to air, it will bend away from the normal. All we need is to do 1 over n is equal to sine I over sine r, because it's moving from more dense glass or plastic to air. So the formula, as a hint, will be 1 over n is equal to sine I over sine r. 1 over n, that's 1 over refractive index, and the refractive index is 1.5. The reason for using 1 over n is because it's moving from less dense, it's moving from more dense, which is the plastic, then from the plastic, which is more dense, it moves into the air, which is less dense. Alright, that's what we do to get this angle, this particular angle where the emergent ray forms with a normal. The continuation of the question says, the frequency of the light produced by the ray is this, 3.8 times 10 to the power 14 Hz, and its wavelength is 5.3 times 10 to the power minus 7 meters, which of course is this millimeter. Calculate the speed of the light in the plastic. Speed is equal to frequency times wavelength, or V is equal to F times lambda. Now we calculate the speed of light in air. Speed of light in air, the speed of light in the glass. We can use the frequency of the, V is equal to F lambda. And then we can find the speed of light in the glass using n equal to speed in air or vacuum over speed in medium. Speed in a glass or in plastic. Speed in medium is approximately 3.0 times 10 raised to the power 8 meters per second. So that's the value we're going to use here. The speed in air is this value, about 3.0 times 10 raised to the power 8 meters per second. And then of course the refractive index is what was given, earlier on. We can use that to find the speed in the plastic. No, this particular question requires us to find the speed in the plastic. We are already given the refractive index. We are given the refractive index. Zoom out. Let me zoom out a bit. This question we're already given the refractive index as 1.5, yes. And we have calculated, we have the refractive index as 1.5. This is given as 1.5. And we have calculated speed in plastic. That's this one. So this is what we're looking for. We're looking for speed in air. It is not approximately this. This speed in plastic is what we have here. Refractive index is given as 1.5. So speed in air is what we calculate. What speed in vacuum is 3.0 times 10⁸, but it's different from speed in air. So sometimes we approximate that to be the speed in air, but it's not exactly that. Now this question says, this figure shows a ray diagram of converging lens forming the image I of the object O. Okay? And of course this image is virtual because the rays do not actually get to where the image is formed. So the question says we should put a tick, let me zoom it out a bit, put a tick in two of the boxes in the following list to describe the image formed. Is it real? Is it virtual? Is it magnified? Is it same size? Is it diminished? Okay. So which length on figure is the focal length of the lens? Circle 1. Which one is the focal length in this figure? Remember, the focal length is the distance from the geometrical center B to the principal focus, where parallel rays pass through. So it will be A to B. The focal length is the distance from the principal focus. This is A is principal focus. And C is the geometrical center. So the distance from principal focus to geometrical center is the principal focus. So it's A to B. So we have this question about mirror. So in this question, you will apply the laws of reflection for a plane mirror. Now, this is the plane mirror. But this mirror is curved. So it might be slightly different. Let me see, the question is on the other page. It says we are to draw two rays, or two rays have been drawn from object O. Draw the normal to the mirror at M, draw the reflected ray at M, draw the ray reflected from P, extend the rays to me to form an image. Okay, this is basically what we're expected to do. So we need to draw a normal at this point. A normal forms angle 90 degrees, so we can pick up a blue pen and draw a normal forming angle 90 degree here. Let me draw the normal properly. That's the normal. So if this is the normal, this means this is the angle of incidence. With this angle of incidence, we can draw the reflected ray. For this ray OM, the ray OM, this is its reflected ray, forming the same angle as the angle of incidence, because angle of reflection is always equal to angle of incidence during reflection. Let me make it better and neater. So it will come out like this. Alright, we can do the same thing for P. Draw the normal at P, and with the normal drawn at P, we can draw the reflected ray for P. You know, OP strikes P and bounces off. So when we make these lines longer, let me remove this because the normal should stop at this point. When we make this line longer, let me make it longer. And make this one longer. Where they appear to meet is where the image is formed. They appear to meet here. So this is where the image is formed. That's where the image is formed. Image. So that's about this. It says draw the normal to the mirror at M. We've done it. Draw the reflected ray from M. Draw the reflected ray from P. Extend the rays back to the right of the image and locate the image, which we have done, and so on. Then this other question is about a light, and there's a lamp here, and that's a mirror. On figure 8.1, draw two rays from the center of the lamp to strike the mirror. Use this to locate the position of the image formed. It's the same principle. You can start from here, draw a ray, it strikes here, and then of course you draw a normal at this point, and the ray reflects back, making the same angle. You show your arrows. You can draw another ray, use a different color, that strikes like this. Also the ray reflects back. Of course you can draw a normal here too. The ray reflects back. Okay, so that it doesn't look like it cuts, let me put the other ray here. I will draw another ray this way, and then I show the normal. You have to indicate with an arrow. The ray also reflects back. And you can see these rays are not meeting. They're not meeting at all. They will never meet because they are spreading out. So what we need to do is we make this line longer, also make this one longer. Wherever they meet is where the image is formed. So the image is formed here. You know, if it is properly drawn, the distance from the image to the mirror will be the distance from the object to the mirror. But this is not drawn to scale. Alright, so that's basically, so it says state two characteristics of the image. Of course, the image is virtual, the image is upright, the image is equal distance from mirror as the object. And it suggests an advantage of positioning a mirror above the lamp. Of course, this will cause the light to reflect and spread better in the room where the lamp is placed. Alright, so these are some of the questions. Do we have any other one here? There might be some more. Okay, there should be some more. Look at this. an object of height, these are further practice questions, an object of height 5 cm forms a real image of height, this with a convex lens, if the horizontal distance between the base of the object and the base of its image is 10 cm, using a scaled ray diagram, find the position of the lens, the focal length of the lens. I will allow you to do this, but you need to, this can form as a hint. Then there's this other question too, the next page. I'll call this one question number 2. This is a hint for question number 2, and then the question number 3. In one investigation, using a convex lens, an object of height 4 cm forms a virtual image of height 7 cm, which is 2 cm away from it. By drawing scaled ray diagram, find A, the position of the lens, and measure the distance between the lens and object. B, the focal length of the lens. You can use this as a hint. Now, in the example in the previous page, repeat the steps with the object height. Now, 4 centimeters. Let me zoom it in. So we're repeating that with the object height as 4 centimeters, the image height as 2.5 centimeters, and the distance between object and image as 8 centimeters. That's this question here. We'll change those values and then practice again. Okay, so this is what we need to do to consolidate on the understanding of what we have done. I've given you some guides, so you practice them